I think I can safely say that nobody really understands quantum mechanics. This deliberately provocative line was in fact spoken by Richard Feynman, one of the greatest physicists of the 20th century. Strictly speaking, it isn't that we don't understand quantum physics. We understand it very well. It's that it is unsettling. Quantum physics looks like no other theory. Our intuition about reality is thrown off course. It shakes our convictions. And yet, it remains the best theory we have today for describing the behavior of matter at the very smallest scales. Despite its strangeness, not a single experiment has ever invalidated any of its principles. Quantum physics, here we are at the borders of the known world. Expect a journey to the far edges of physics. But before diving into the heart of matter, what are we talking about? Quantum physics lets us describe physical phenomena at the atomic level. Thanks to it, we understand better how the different particles that make up matter are structured and how they interact. Look at this pétanque ball. It appears whole, solid, compact. And yet, like everything in the universe, it is made of billions upon billions of tiny bricks fitted together. Atoms. Atoms have a complex structure, a compact nucleus surrounded by electrons, tiny particles with a negative electric charge. For a time, we pictured them like this. Small balls orbiting a nucleus, a bit like a planetary model of our solar system. You can see that these atoms are mostly empty space. Here's the puzzling part. If the atoms that make up everything around us are largely empty space, why can't we slip between their nuclei and pass through matter? If our pétanque ball is made of atoms, so of empty space, it should even be able to pass through the table. To understand why it doesn't, we have to look at this. A more recent, more accurate representation of what an atom really is. In this newer model, electrons are no longer little balls orbiting a nucleus. They're hard to pin down, nowhere and everywhere at once in a kind of electron cloud. To put it very, very simply, it's as if each of these clouds were an electron's airspace, a sort of force field, and the others aren't allowed to enter it. That's why we can't walk through walls. All of this, we have to admit, must be accepted without being directly observed. Few people have the equipment at home to verify it. So how did we figure it out? Scientists first detected their presence, rather like footprints in sand tell you someone passed by even if you didn't see them. From there, they followed the trail. Today, we can not only observe atoms, we can also manipulate them. Remember that even the greatest scientific theories are often built from a handful of faint clues noticed by a small number of researchers around the world. And this journey began about 120 years ago. At the end of the 19th century, physicists were convinced that almost everything had been discovered. Physics seemed to hold no more secrets. Newtonian mechanics, electromagnetism, thermodynamics. By century's end, humanity believed it knew and mastered all the physical laws governing the world. As Lord Kelvin told the Royal Institution in London, knowledge in physics resembled a vast blue sky on whose horizon only two small clouds of misunderstanding remained. As we'll see, Lord Kelvin was far off the mark. The scientific world was in fact on the brink of a revolution. To understand why, let's go back more than 2 centuries and look at something simple. Light. Is it really that simple? Aim a narrow beam of light at a glass prism and you'll see that it's actually made of a whole spectrum, a kind of rainbow from red to violet. And that's just the beginning. For some scientists, such as Isaac Newton, light is a stream of billions of microscopic grains, corpuscles, that move in straight lines. This is the corpuscular theory of light. To visualize it, take a paintball gun and fire at a projection screen through a kind of stencil, a vertical slit cut in a wall. The paintballs that pass through the slit will form a more or less sharp vertical mark. Light grains would behave much the same way. For other scientists, notably Christian Huygens, light is a wave. That is the wave theory of light. Very simply, a wave is a propagating disturbance. Sound, for instance, is a disturbance of air that presses on our eardrums. Ocean waves are vertical movements of water molecules caused by a traveling oscillation. To get a feel for it, watch this wave tank. Waves generated on the left cross the tank, alternating highs and lows with some number of oscillations per second. If we place an obstacle with a vertical slit, look what happens. The waves change shape and become concentric. We say they diffract. They're strongest in the center of the tank. We say their intensity is higher there. Now remove the water and replace the wave generator with a light source, say a laser. If light consists of a stream of particles like paintballs, we should get a fairly sharp vertical streak. If, on the contrary, it's a wave, the slit will diffract the light and the streak will be broader, fuzzier. So, what do you think? Light, wave, or particle? Why ask such questions at all? In the 19th century, physics was more than adequate to run steam locomotives, float ocean liners like the Titanic, and, generally speaking, make sense of the world. But that's precisely the scientific spirit, to keep pushing the limits of knowledge. And this seemingly trivial question about the nature of light, one that might even look like an idle scientific whim, would lead straight to a revolution. We're at the dawn of the 19th century, 1801 to be precise. In London, a scientist is about to perform an experiment that 2 centuries later, in 2002, would be voted the most beautiful experiment in the history of physics. Thomas Young, a British physician, physicist, and Egyptologist, simply passes a beam of light through 2 parallel slits and projects it onto a screen. This simple experiment will help reveal how light works and what it is. Here it is, Young's double-slit experiment. It's roughly the same setup as before, but with 2 slits. That's all. Let's bring back our tank, without water, and our paintball gun. Fire at the screen and observe the result. 2 nice vertical bands right behind the slits. Now swap the paintball gun for a laser. Logically, if light is made of little grains, it should act like the paintballs and form 2 vertical bands. Here we go. And there you have it. Surprised? That isn't what we had reason to expect. There aren't 2 vertical bands, but a whole series, evenly spaced, like a luminous barcode brightest at the center. Strange, isn't it? Now, back to the wave tank. This is where it gets interesting. Watch how the waves behave beyond the 2 slits as they diffract. They collide. We say they interfere. In some places, crests and troughs line up and the wave is amplified. Conversely, when a crest coincides with a trough, the waves cancel out. These are interference effects. Now look at the projection screen. The alternation between amplified and canceled waves forms what we call interference fringes, and they look exactly like our light barcode. The experiment is unambiguous. Light is a wave. So Newton was wrong? Young's observations are compelling. Light is a wave. The long-running debate in scientific circles seems settled. A little later, in 1839, the French physicist Antoine Becquerel and his son present the results of their research. Under certain conditions, light appears capable of influencing the electrical behavior of metallic materials. The effect is clearly visible experimentally, but it is very hard to explain precisely using classical physics equations. Today, we know this phenomenon as the photoelectric effect. Let's try it. What is the photoelectric effect? Take a metal plate and connect it to an electroscope, a device that measures an object's electric charge. The needle doesn't move, the plate is electrically neutral. That is, each atom has just the right number of negatively charged electrons to balance the nucleus's positive charge. Now shine a desk lamp on the plate. Nothing happens, the needle stays down. Even if I increase the lamp's power, its intensity, nothing happens. So far, not very impressive. But if we replace the desk lamp with an ultraviolet spotlight, the kind you'd find in a nightclub, watch what happens. The electroscope responds. The needle climbs higher and higher. The plate is losing electrons. We could even channel this stream of electrons, this current, to, say, light a bulb. Under certain conditions, light can generate electric current. When scientists first discovered this, they were baffled. If light is a wave, then simply increasing its intensity, its power, should trigger the effect and knock electrons loose, but apparently not. However, when the light's color changes from orange to violet, electrons are torn from the plate. A light's color is tied to its frequency. Watch what happens when I use a color dial. To generate an electric current with light, it's not a matter of power, but of frequency. That may not seem like much, but this conclusion is a problem, at least for classical physics. It flatly contradicts the known equations. At the end of the 19th century, while trying to explain the frequencies of the light emitted by stars, the mathematician Max Planck inadvertently threw a stone into the pond. He found a solution to his problem. But for the equations to work, light had to be made of tiny, indivisible packets he called quanta. For him, this notion was a mathematical trick, a way to make his equations behave, but physically nonsensical. For a young German-born physicist unknown to the public, however, it might mean much more. In May 1905, Albert Einstein published a paper for which he would receive the Nobel Prize 16 years later. It dealt with the photoelectric effect, with light, and with quanta. Einstein, known to everyone for relativity, did much more than that. For example, he was the first to successfully explain the famous photoelectric effect, and his explanation would cause quite a stir in the scientific world. According to his hypothesis, without denying the wave theory, light is also made of small packets of energy. These are the very quanta introduced by his colleague Planck. When speaking specifically of light's quanta, we use the word photon. Simply put, in Einstein's view, light is a stream of photons. The higher a light's frequency, the greater each photon's energy. To visualize, imagine a target shooting contest with a cannon. The lamp is the cannon, the photons are the cannonballs. A frequency dial lets us fire projectiles of different colors. For instance, low-frequency red cannonballs have less energy than violet ones. Our target is the metal plate, or more precisely, its electrons. The goal is to knock out as many electrons as possible to create as much electricity as we can. Start with the photons from our desk lamp, so with a rather orangish frequency. Even if we crank up the lamp's power, we only get more orange photons. The electrons still won't be ejected. Okay, change the light's frequency to get violet. Now we're talking. Once we've reached the right frequency, we can increase the intensity. In short, only by exceeding a specific energy threshold, a cutoff, does a photon's impact on the plate expel an electron. In Einstein's hypothesis, light thus behaves like a stream of particles. Remarkably, this doesn't invalidate Young's result. Light would therefore behave both as a wave and as a stream of particles. This is the wave-particle duality of light. With quanta and duality, the world steps squarely into unknown territory. For classical physicists, it's like being told something can be hot and cold at the same time. Over the following years, more and bolder researchers would explore this theory. People began to speak of the theory of quanta, then of quantum physics. A new current swept through classical physics, profoundly overturning it. Soon, a debate, more philosophical than mathematical, pitted scientists against one another, notably Einstein and his Danish counterpart Niels Bohr. How should we interpret the baffling implications of quantum physics? By the 1920s, another question arose. If light is both wave and particle, is the same true for other corpuscles, like electrons, atoms, and thus matter in general? Let's try the experiment. Replace the laser with an electron gun capable of emitting a single particle at a time. For each emitted electron, a tiny bright dot appears on the screen, just like the paintballs, but over time, impact after impact, these dots build up an interference pattern like our light barcode. So electrons behave like photons? If you remember wave-particle duality, you can feel we're entering turbulent air. Buckle up. Electrons seem to act like a wave, but abruptly behave like particles the moment they hit the screen, or any device that observes them. And it's impossible to predict precisely where they will materialize. It's as if, before meeting the screen, they didn't really have a definite position. At best, we can compute the chances of finding them here, or here, or here. To keep it simple, once emitted, a particle behaves like a wave, but as soon as it is observed, it shows up as a particle, a kind of subatomic game of red light, green light. This wave-particle duality of matter is one of quantum physics' most counterintuitive ideas, and you're only at the beginning of the journey into the strange. If you try to determine which slit an electron passes through, for example by placing a tiny detector, the interference pattern disappears. The electrons stop behaving like waves and behave like particles. They make two bands right behind the slits, like the paintballs. Remove the detectors and the interference returns. It seems crazy. The very act of observation appears so intrusive that it disturbs the experiment. I know, none of this is easy to accept. In 1935, the physicist Erwin Schrödinger imagined a now famous thought experiment. In it, a cat is shut inside a sealed box with a vial of poison. Inside the box, the poison can be released only by a trigger tied to the quantum state of a particle. The poison is both released and not released. The cat is both dead and alive.